Okay, so reference is still zk book. So last time we covered QAP, right? So recall that we start from the beginning for graph 16. The first series was we discussed like a graph bipartite proof, right? Remember that, right? That was the problem statement. So our objective is to generate a zero knowledge proof for the bipartite problem, and then we turn that into R1CS and recall that it was the matrices representation, right? So the matrix was called L, R, and O. So L times A Hadmar product R times A equals O times A, right? That was the equation for R1CS. And last time we covered how to use Lagrange interpolation for, no, that was probably the week before, right? We covered how to do that and compress the R1CS matrices into UVW, which are, they are arrays of polynomials, right? So we are compressing each column vector. So we take each column vector from R, L, R, and O, and squeeze them into polynomials using Lagrange interpolation. So for each matrix, we had 5 columns, right? So we do interpolation 5 times, and so each array should have like 5 polynomials, right? So last time we talked about QAP. We proved the QAP formula. So it was the like U times A parentheses times V times A equals W times A plus HX times TX, right? Yeah, that was a QAP formula. So we also discussed the Schwarz Zippo lemma, which says we don't have to compare, like for example, my objective is to compare the equality between 2 polynomials. We don't have to compare coefficient to coefficient because that's gonna take too long time if my polynomial is huge, and that contradicts with the definition of SNARK, right? So I talk about the observation behind Schwarz-Zippo, and we can just evaluate the polynomials at some random point, and we got the number, and we compare the number using pairing. Right? That was the idea. So last time the problem was the random point. How do I keep it secret? Because first, these random points must be random, right? So it has to be generated by some person. So first has to be random. Second, if I leak this value to the prover can generate a fake proof to trick the verifier. Therefore, I have to quote unquote encrypt this number. Therefore, prover cannot generate like some like fake proof and send to the verifier, right? So the idea is to use a trusted third party. So in literature, this is called trusted setup ceremony, right? So it is required by every single SNARK. I think so. Okay. So in graph 16, we require a circuit specific trusted setup. So that is the downside of this protocol, because in Plonk, we can use a universal trusted setup, which saves some work. Because if you go into Circom and SNARK.js, you try to generate that trusted setup powers of tau, it's going to take a long time. Therefore, it is better to just generate that once and use it for like many circuits, right? So that is the advantage of Plonk, and therefore Plonk is the Plonk and Plonkish family, like Plonky 1, 2, 3. They are the most popular framework right now, and Graph 16 is rarely used because it requires circuit-specific trusted setup. So today we are going to derive some formulas behind this powers of tau stuff. Okay, so so the first question is, why do we need to encrypt them and keep the random point secret? Because if you leak this value to a prover can just like generate this number. Like he can just pick some random numbers here, right, to satisfy this equation, and then he can generate a fake proof, and that is unwanted, right? So this tau is a secret number. So in literature, I believe it's called toxic waste, right? So after the trusted third party generate this number, that party must discard this value and delete it permanently. So it won't be leaked to some like attackers in the future, right? Okay, so how does the trusted setup look like? So the format looks like powers of tau. So why is it called that? Because it is a list, right? So powers of tau starting from power of 0, so tau to 0 to tau to 1, and we have to generate 2 of them. So I recall that in the last step, the verifier step, we have to compute a pairing which takes a G1 point and G2 point as input, right? So pairing, you have to generate 2 points. So on the left-hand side, you have one pairing, right-hand side has a pairing. So in total, you need four points, and 2 of them are G1, 2 of them are G2. Yeah, so in this step, we are trying to convert the QAP formula into those G1 and G2 points. So in practice, when if you are trying to implement this code, you have to make this label really, really clear because it's confusing, so at this step, like everything happening here is either a G1 point or G2 point. Therefore, this is the notation I use. So I use like a bracket and a label either 1 or 2 to represent G1, G2 point. Right. So if you read zk book, the formula is kind of convoluted, like in my notation, just remember this bracket is always a G1 point. So what is a G1 point? It is some G1 times some scalar, right? So the thing behind, like before G1, it should be an integer. Oh no, I mean it should be a field element in the scalar field, right? So this is on scalar, and if I write it in bracket 1, then it's a G1 point. Okay, so yeah, just follow this notation for now. Yeah. So what we are computing right now, it is A, B, and C. So what are they? They are, for example, A1 is computed in this way, right? So basically A1 means we evaluate U times A. So this is the first term in the QAP formula. We evaluate that polynomial. So recall that this is the interproduct between a polynomial and the witness vector, right? So basically here, I mean, you take that array of polynomials in U and take the array of witness, you compute the inner product. So U times A means the inner product between U and A, and it is still a polynomial, okay? So what we are doing here is to evaluate the polynomial at tau. And I claim that the prover can compute this effectively and without knowing what tau is. So how does it work? Let's see the the formula. This is pretty easy. Okay, this is just middle school algebra. So the only confusing part is the notation. Okay, so remember that we are evaluating, we are trying to compute a given point. So the result is given point. Okay, so we put this bracket like outside. Okay, so first step here is we expand the inner product polynomial into some common form, because we know that a polynomial always look like this. So the Cn to C1, they are the coefficients of the result of the inner product. Okay, so yeah, evaluate the polynomial at tau and then compute the given point. And next step, we evaluate the polynomial at tau. So just plug in this x as tau, right? So this is the result of the evaluation. And then this is still given point. So at this point, we are doing EC point addition. Recall that this identity just comes from parentheses a plus b times g equals ag plus bg.
Sorry, Chen Yan, can I ask a quick
Yes,
question?
yes, please.
You said that tau would be removed, or it's like toxic waste. So, like, how are you
Yes,
using
yes.
it at this point?
So this tau right here is a symbolic tau. Okay. So yeah, if you follow the formula here, you see that we don't need this tau. Why? Because I can break down this calculation into a series of EC additions and then factor out the scalar out, right? So you see here, like the first term becomes Cn times tau n times g. Yeah, I think I should say like G1 here. Okay, I forgot to put G1 here. So this is Cn times tau n times G1, and it is a part of the chassis setup. Yeah, just this one. Okay. So you see that we are plugging in this number. So this is a given G1 point. We just plug in the number here. Therefore, when the prover computes this A bracket, he is computing an inner product because he knows this Cn minus 1 till C. Yeah, I should. Oh man.
Yeah, okay, no, that makes sense now that you've shown
Yes.
the next two equations. But now I'm just trying to figure out, if you don't get rid of tau, then how does that
Yes.
allow the prover to forge proofs? I think that was the terminology.
That is very good question. I was thinking about it, man. I was thinking about it. So in zk book, there is no explanation, right? I think Jeffrey just mentioned this, like it should be a secret, but I think
Yeah, from
we
the
can do
equations point
some.
of view, could you figure out something? Because I haven't explored it
Yes,
myself.
I think you can figure out something here, right? But I don't know how to explain. But the idea is, if prover knows tau, then he can forge a fake proof, possibly like infinitely many proofs from here. But how to do that in formula, I haven't figured out.
Okay,
Okay.
cool. No, even I'll try it later and then let you know.
So yeah, I think I need to like for example, say I can generate one correct proof here, and I can also generate a fake proof here using two sets of notations. But I haven't figured out how to do that in notation. But I'm pretty sure that if you know tau, you can do like many combinations here to satisfy this equation. And in the end, since verifier only verifies the pairing, you only care about that, like the scalars in pairing, right? So recall that pairing of, for example, of 5G2 times 6G1, right? So the scalar, the product of the scalar is 30. So somehow the attacker can do a fake proof here. Somehow, yeah. yeah, I'm gonna leave a note here. I can figure this out. It's called question how to generate a fake proof if tau is leaked. Okay. Yeah, I'm gonna figure this out. Very good question. You caught me.
Sorry, no, I don't mean to put you on the spot. It's just I see the equations and it's just interesting to.
Yeah, I know, right? Because I didn't have time today.
Okay, no, it's okay. I'm sorry. Yeah, you can continue. I just wanted to.
Yeah, today we were discussing the 30K drama with Kraken, and we didn't have time to figure this out. Okay, anyway, so 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 take this as a fact for now. Okay, so the idea is just you have to keep tau a secret, and the computation is just an inner product between these coefficients and the entries in the setup. So the prover, he doesn't need to know what tau is. Okay, so this is exactly the same idea as KZG. So if you read KZG, the idea is yeah, the same. Okay, so you learn two protocols at once. Okay, so yeah, and if you want to implement this, always keep this symbol clear. Okay, so you know which point is G1, which is G2. So G1 point, I see. So this is like a 2-entry coordinate. Okay, so G2 point will be like 4 entries because the Weierstrass equation of the underlying curve involves a complex number. Therefore, you need 4 entries. Okay. So you see, okay, we have A1, B2, and C prime 1, HT1. So why is that? I think this is just a convention. Okay, so you have to make sure on the left hand side and right hand side, one term is G2 and one term is G1. But what if I say, okay, if I do A2 here and B1 here, I think the result will be the same. But yeah, this convention is just we follow the paper and follow the notation there. So I don't think it really matters. Okay, so the idea is just you have to have a G1 point, G2 point in order to compare the pairing. Okay, so C1. Now, I mean, C prime 1 is the transformation of W times A. Okay, so you also have that term HX times TX, and this part requires some additional discussion. We will discuss it later. So there is some problem here basically because we are evaluating polynomials twice. So this becomes H tau times T tau. And if you evaluate that twice, you have to, that is saying you have to multiply two EC points. Therefore, it will involve pairing. But in prover phase, we require that there is no pairing because the pairing part should be done by the verifier only. So the prover, everything he computes must be either G1 point or G2 point. Yeah, I have to make this very clear. Okay, so there is some problem here, but it doesn't matter. We're gonna figure it out later. This C1 is the sum between C prime and HT. So the equation. So this will be the final equation for this session. Okay, so in the next session, I'm gonna cover why this is broken. So attacker like a malicious prover can attack this formula. Okay, so that will be the story of alpha, beta, gamma, delta, RNS, and that will be the next session, which is the last session. Okay, but for now, this looks pretty good for like this construction. Okay, so this looks very clear that in the end verify into pairings, and this is very easy to do if you for example, you can do this in a Solidity contract. This is super fast. Okay, so you just call precompile 0x8, which is called the easy pairing precompile, and you just feed in all the coordinates here. So following their rule, okay, so they have a weird rule, so you just feed in all the coefficient. Feed in all the coordinates, and you get the result here. So it's either 1 or 0. So true or false, returned by that precompile. Okay. Okay. So this is good. Okay. So the next discussion is why is that this HT term needs some special discussion, because I already told you, if you evaluate that twice, you have to compute the multiplication between two given points, which involves pairing. Okay, so this is pretty bad. I think I need to highlight this. So in the ZK book, the explanation isn't very clear, because when I was reading this part, I was thinking, so okay, you are telling me that if I evaluate two polynomials, then it becomes complicated, right? But what if I just compute hx times tx symbolically? So I'm not evaluating anything right now. I just compute this polynomial, which is always computable. Okay, so I can compute this hx times tx, and the result is another polynomial, and then I evaluate the result at tau. Like, how about that? I was thinking about this today. I think the idea is you have to minimize prover time. Okay, so if you let the prover compute a product of polynomials, I assume the only way is do a double for loop. So compute like the first term of the first polynomial with like every term of the second polynomial, and then you loop through all the terms in the first polynomial, right? So that will be a double for loop, which means is O(n) squared time complexity. Okay, so we don't want this one single operation to mess like everything up, because the operation we have done before, they are pretty fast. And if I introduce something of O(n) squared here, then my whole algorithm will be O(n) squared minima. Okay, so I think the idea is to skip all the expensive computations, and therefore we say, oh, we have to evaluate first. We cannot just simply like multiply two polynomials. Okay, so I think this is the idea. This is my own thought. I don't guarantee if this is correct, but I think pretty much. Okay, so the solution is to embed this t tau into another chassis setup. So recall that we already have these two arrays here, right? They are pretty clear. Okay, so we already have these two chassis set up here, powers of tau. We are going to introduce another powers of tau. So the only difference is I'm going to embed this t tau value as a scalar before G1 in every term, and unchanged, just t tau, like times everything before G1 here. Okay, so why does it work? Let's see the derivation. This derivation is pretty similar to the one we just did. Okay, so I think the confusing part is here, like the first two lines. So we are evaluating h tau and t tau as a G1 point. So it is very easy to see that it equals h times t, and then evaluate tau, right? But this is this is pretty expensive to multiply h and t first, as we discussed here. Therefore, had to change the idea into the expression in the second line. So here, so why does this equals to this? I don't have a proof, but I can show you an example, right? So for example, tx equals x minus 1, hx equals 2x plus 1, and I evaluate both polynomials at 5. So tau equals 5. If we compute the left-hand side, like this expression here equals 44, okay? Pretty easy to do. If you compute like this, this thing on the right-hand side, it is 2x plus 1 times 4. And then you symbolically evaluate this as 8x plus 4, and then plug in the x, which is tau. And then you plug in this 5, it becomes 44. So this equals to this. Okay, it's not a proof, but it's an example that pretty yeah, I'm convinced at least. Okay, so this is pretty random example. Okay, so you can see if we are computing this expression is the same thing as computing this, exactly the same thing. Okay, so why this is better? Because we already have this t tau information in the power tau, like the third power tau, right? So yeah, you see the derivation is pretty much the same. So we expand this hx into a generalized polynomial form, and then times t tau. So this is just a constant, okay? So yeah, you can multiply this constant by every single term here, and yeah, expand this further and say, I'm going to evaluate the entire polynomial at tau and then compute the G1 point. Okay, so this is, I plug in this tau for every single x here. So this was a polynomial and this was just a number now, okay? And evaluate as a G1 point. You can break down the EC addition and like split this out, like every single terms here, and then factor out this h0 because this is a scalar multiplication. You can factor this out and say, okay, I'm gonna do this as G1, 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 and all these terms, they come from the trusted setup here. So that's why this is useful. And we solve the problem. One, we solve the problem of a potential pairing. Second, we don't have to do the polynomial multiplication. This is very expensive. Okay. So okay. Do we have questions so far? This is all the theory part, and after this is just Python. Yeah, I think.
Sorry, just a quick question. What was the benefit of reaching this last step right now?
What's the benefit of reaching the last step here?
Yes.
Okay. So the benefit is if I don't do this, and also if I don't do the trusted setup here, I'm going to have to compute h. So h tau times t tau. I have to compute this directly, which means I need to do like multiplication between two G1 points.
Yeah. Okay.
Okay. So if you do this first and then do t tau first and then compute the G1 point, you have to be like h tau G1 times t tau G1. You can't even compute that, right? Actually, I'm a little confused too. After you asked me the question. Wait. Man, you asked really good question, okay? This is a really good question. I think I'm confused too. I gonna figure this out later. Don't worry, I gonna figure everything out. So the question is, what if, you mean what if I evaluate H tau, P tau directly without doing the actual power cycle? This is a really good question. Okay.
Was this
I
the
thought,
approach that
yeah.
you came up with, or is this
doing
something that was in the papers that you?
multiplication. I
So this is the
see the
official
space of
solution.
example like that.
But like the motivation part is I come up with. Okay, so the solution is official. Okay, so this part is official, but the derivation is done by myself. So like these derivations are done by myself, and also like the motivation behind it is done by myself. Therefore, I cannot guarantee if my thought is entirely correct. Okay.
Okay, thank you.
But if you want to search this on the internet, I don't think it is actually there. Okay, so if you search like why this paper implement this, I don't think it's gonna be an easy question to answer, and also I don't think it can be easily found on the internet. Okay, so because like very little people like discuss this kind of stuff, and most of the articles on the internet, they just list like how this works, okay, without explaining anything. That's what I found. Okay, so I gonna think about this one more time, but I think I'm pretty close to the final answer. I think the final answer is you have to deal with the multiplication between two given points, but I don't see how that works mathematically right now. Okay, so I gonna derive the formula for this claim. Okay, so far this is a claim. I have to prove it, use math, and I have to prove the other question you asked with actual math. Okay, so okay. But you understand the general ideas, right? So the main ideas in this setup is just because I don't want to do expensive computation, I'm going to delegate this job to some like other people, to a trusted third party, and I delegate this job to him. I have to trust him to publish all the correct parameters, and then I use this parameter here, so I only compute the inner product, and therefore my computation is super fast. And yeah, I think that's the main ideas to understand. These two questions are details. Okay, I'm gonna figure this out. Don't worry. Okay. That was the theory part. After that, let's see how it's implemented in Python. So I think this is very easy to understand, but if you are not familiar with this list comprehension in Python, I provided an example. So list comprehension, the syntax. Okay, so the syntax is I don't want to do a for loop, therefore I use this list comprehension to represent a for loop, right? So I write the for loop here. So for something in an iterator, and then I compute this expression for every single entry in the list, and I have a like optional conditions. If conditional, I gonna do that. So yeah, maybe it sounds confusing, but let's see an actual example. Here, the new list is power. No. I mean 10 times x for x in range 5. if x is odd. Therefore, so in this range, it includes 0, 1, 2, 3, 4, right? So the only odd numbers are 1 and 3. If you compute this with times 10, then it becomes 1 times 10, 10, 3 times 10, and 30. Okay, so or you can just omit this if part to have this generate like 0, 1, 2, 3, 4 times 10 for each entry. Yeah, I think this is pretty easy to understand, right? So the code here is just the same as what I did before. So this tau should be a field element, right? So field elements to the ith power. So this corresponds to this formula. This formula, okay? So tau to 0, G1, tau to 1, G1, and the first was times G1, the second is times G2. Okay, so the powers of tau are the same and the G point are different. So at least comprehension. So in this range, okay, so this t degree is 2. Oh, no, I mean theta degree is 6, and then for I in range 6, so 0, 1, 2, 4, 5, and you compute this comprehension. This means the scalar multiplication, right? So I'm multiplying this number to G1. So just be careful that in PyECC library, you have to write G1 or G2 point before. So you cannot say, okay, what if I flip the order? If I flip the order, code won't compile. I mean not compile. I mean it is not going to run because it's not a compiler, it's interpreter, right? So yeah, have to remember that detail, right? Just put G1 or G2 point in front and then do, okay, powers on top, multiply G1 point or G2 point. And the only difference here is we embed this t tau value. So it is this, okay? So we embed this t tau value in every single entry. And don't worry about the delta. We're gonna talk about delta next week, okay? This is very easy to understand, right?
Why is the degree 1 less for the last one?
Oh, it's just because in the paper it's defined this way. Okay, so if you ask me why, I'm pretty sure that it has something to do with the constant term, I think. Right, because, wait, let me see. Oh man, you ask very good questions.
I'm sorry, like it's just like it's curious.
You got me confused again.
It makes sense when you showed us all these equations, but then it's just not matching right now.
I'm pretty sure it has something to do with the constant, right? Otherwise, why is one less? Yeah, I'm pretty sure the implementation is correct because my code works. Okay, it is tested. It definitely works. The formula is correct as well. Man, you got me, man. I need to figure this out. It has n+1 constant. No, I mean n+1 coefficients here, right?
But the last
this
term
is
does
n+1.
not have a tau term.
Oh man, I don't know. Let me write this down. Oh god, let me write this down. Third question: why the third powers of tau has one less term? Okay, I'm gonna figure this out quickly today, later. Okay. I don't see why right now because maybe this formula isn't correct as well, the derivation here. Maybe I put like one extra term here.
Yeah, maybe, I'm not sure either.
Oh, okay, I'm gonna figure out later. Don't worry. Easy. This is small detail. Okay, small detail. Yeah. Let's move on. We implemented all the powers of tau generators here. So the next step is to evaluate polynomials with the powers of tau. Okay, so these functions are the evaluation functions. They look like the same. Okay, so you first generate the powers of tau using the functions we defined here, and then just do inner product. So everything here work in the same format. The polynomial coefficients, this one, so in Python, this means like reverse everything. So reverse the order of a list or a tuple or something. Okay, so this means reverse. Why do we do that? I think it's because the poly here is represented in like a flipped order. Yes. So I believe this poly in the code works from like higher terms to lower term. So the coefficients will be like cn minus 1 till c2 c1. But our implementation here is I start from the lower term. So therefore you have to either flip the order of this list. So you either flip the powers of tau or you flip the coefficients of polynomial. But I think in the paper, I had to respect the order of powers of tau, and therefore I flip my polynomial coefficients here. Okay, so I think the only confusing part here is how do you explain this code in inner product, because this like reduce, we already talked about that last time. So reduce means you just, like for example, if you do add and 1, 2, 3, 4, 5 here, then you are evaluating 1 plus 2 plus 3 plus 4 plus 5. Okay, that's like simplified explanation, but we already like discussed this last time. So yeah, I think this is good. Okay, so the first parameter is the function, right? So add is the function. And this part is pretty confusing. So from this parenthesis, like the green one here to here, this is pretty confusing. Okay, so this is, in Python, this is called the generator comprehension. So the idea is pretty similar to list comprehension, but this outer notation is parentheses. Okay, so this is called generator comprehension, and compared to list comprehension, the advantage is it saves memory, because when you do list comprehension, Python is going to reserve a part of the memory and then just compute everything and put everything into the memory, and after that you can do random access. Okay, so that is list comprehension. But if you do this generator comprehension, it is creating a generator, which means I only tell you a formula for computing the next element. I'm not going to pre-compute like everything and store everything into memory. I'm going to tell you a formula for computing the next one. So the idea is kind of similar to a linked list. Okay, so I provided an example here. So for example, if I want to generate every even number between 0 and 99, I'm going to do this. Okay, so parentheses. So I for I in range 100 if I is even. Okay, so this is going to give me an generator object at some memory location, and I cannot do random access. The only thing I can do is calling next, or I can just wrap this generator as a list or something. Then it becomes the same as list comprehension, right? But the intended way to use it, I think, is call this next. So you have this 0, 2, 4, 6 here, and so on and so on. But Python is not going to pre-compute everything and store everything there. So the reason why we use this code here is because if you pre-compile, if you pre-compute this thing, it is pretty time-consuming, I think. Right, so we are computing a bunch of C1 or C2 point, and we are going to do that for many times here. If we store everything in memory, this code will be very inefficient. And yeah, the good news is our problem is small because we only have 7 constraints, right? But think about if you have 30,000 constraints, right? So this is mainly for optimization. This generator comprehension thing is, I think this is not is not often used, but it's pretty nice to know it. So this is a thing, okay? The other confusing part is zip. So in Python, this zip, in my understanding, this is just a Cartesian product, right? So here's an example, right? So the first list is ABC as a string, and the second list is 1, 2, 3, 4, 5, 6, 7, 8, 9 as integers. If I do zip on them, it's going to return me a zip object at some memory location. If I cast that to a list, I will see, okay, I have 3 ordered pairs. So entry 0 and entry 0, they are put into a order pair. So this is in math, this is just a Cartesian product between 2 sets, quote unquote sets, okay? I think this is pretty easy to understand. So I'm going to, so what I'm doing here, right, is to compute the inner product. Therefore, I'm going to compute a list of ordered pairs, and then I multiply them. And I first have to cast this field element to integer and then multiply them, okay? So, and for optimization, I have to put them into a generator because I don't want to store everything in my memory. And therefore, this nested code means, right? So up until here, between the green parentheses, the code is doing term-wise multiplication. Okay, so when I finish this, I got a generator. Then I put this as an input to reduce, and I'm going to add recursively on each term. And if I want to make this happen, I have to say, okay, so when I do addition, I need to add it to Z1, which means the point at infinity, which is the identity element. So this part is really just, I want to take the sum of of every element in the generator, but I can't do that because I don't think sum works on this generator, okay? So I need to work around. So how do I do that? I feed this generator as input to reduce. I have to do recursive add, but with the identity, which means I need to satisfy the Python grammar. Man, this is hard to explain, but I think you understand, right?
Yeah, the idea is a little clearer. There's a question in the chat regarding what
Yeah.
this reduce statement does.
Okay, so I have this in last week's note. So it basically means, like, for example, I have a list here, A, B, C, D. Okay, so if I say, okay, so reduce parentheses add comma list A, B, C, D, that means, okay, I'm gonna do A plus B first, and then so the first iteration is I do A plus B, and then I take this result. In the second iteration, I do A plus B plus C, and in the last iteration, I do A plus B plus C plus D. So this reduce is kind of like folding an iterator down to a single element using some function here. So if I do multiply here, I'm going to multiply all the elements in the iterator together. If I do add here, I'm going to take the sum of the iterator, like every element in this generator. Okay. So does it answer your question?
It was asked in the chat, but yeah, I think just
Okay,
seeing more
okay.
concrete examples would help. But yeah, you did paint a good.
Yeah, I had this in last week notes, and also if you just Google Python reduce, I think there are plenty
Yeah,
of examples there.
sure we can find.
Right?
Yeah, I haven't seen last week's notes yet, so
Yeah,
I mean,
I know you weren't here. Okay, so yeah, I think that's everything. Yeah, that's everything. So this week, the idea is to evaluate polynomials at some random point, and also we need to keep that random point secret. Okay? So that's the idea for this week. Next week we are going to cover why this formula is wrong. So this formula right now is very vulnerable. Next week we are going to break down the session into 3 parts. Okay, so we are pretty close to the end of graph 16, but there are 6 additional parameters used in the paper. They are called alpha, beta, gamma, delta, and RNS. So alpha, beta is the first part, and gamma, delta solve another problem, and RNS solve another problem. Okay, so next session we are going to break down the formula into 3 parts, and we ask, okay, so what if I don't use alpha, beta? What if I don't use gamma and delta? What if I don't use RNS? And we can come up with three types of attacks. And for each attack, we are going to introduce a new set of variables, parameters, to solve that problem. And in the end, we will have fully worked end-to-end graph 16 code. Okay, so that's the plan for next week. Do we have questions for this week? I think it's pretty clear now. I already recorded the question asked, so there are 3 questions. I'm gonna figure out this later. Okay. Do we have more questions? I think no, right? Yeah, this is pretty easy to understand compared to the book or some random article on the internet. I think this is very approachable. Okay, so if
how long
no
does it take you
question,
roughly to like work through these?
you mean how long took me to learn like everything from the beginning? I think it's close to like 2 months, I think, right? Because yeah, I think 2 months. But it's like part-time work. I don't do full-time study. Okay, so about 2 months, 8 weeks. Yes, pretty close. Like about 10 to 20 hours per week, because I was doing auditing at that time. Yeah. Okay, so yeah, we are just on time. 1 hour session. Nice. Gonna stop sharing. Okay.
Thank you for the session.
Okay, so yeah, if no more question, I'm going to see you guys next week. And yeah, of course, I'm going to share the notes. I'm sharing right now. Good.
I think they also get uploaded on the website within the next 20.
Sure. Yeah, I will tell Gaylord about that. Okay.
Thank
Nice.
you.
I will see you. You are welcome. See you guys next week.